Hello everyone and welcome back. So in the last lecture, in the last few lectures, we have covered what do we mean by blurring in the first place, how can it be deduced from geometric optics, like how can we deduce the extent of blurring from simple geometric optics, how can then we define the blur circle and how the light is redistributed within the blur circle using point spread functions, and then how point spread functions can be implemented in the systems, to emulate blurring in imaging systems by an operation that is known as convolution. So that is what we have done till now. So we ended the last lecture on the note of discussing this application to uh, blurring of a particle image. So we will start from there in this lecture. So with all the fundamentals that we have learned, now we will apply it for the problem of blur image formation, especially related to dispersions or particles. So here we consider an axisymmetric like round particle, which looks like a circle in the projected image, and that is represented by the solid blue line here. So this is our focused image of the particle, and it is blurred using a Gaussian blur kernel, and we operate this kernel in a convolution to generate the blurred image, and that is represented by this equation. So IF is your focused image, H is your blur kernel, and G is your intensity map in the blurred image. And we can define the IF, that is the focused image, in a mathematical form like this. So as it is a circular particle, so it is easier to choose a polar coordinate system. And in that system, when the radius is less than the radius of the particle size, that is r naught, then we assign a value of 1. And for the rest of the image, we assign a value of 0, which is an illustration of the background. And as you can see, we are using zeros and ones, and all the other intensities, even in the blurred image, will lie within it. So we are normalizing the intensity in the range of 0 to 1, where 1 represents a shadow and 0 represents a background. Okay. And this convolution equation, when written in the form of, say, an integral equation, will look like this. So earlier when I showed you the convolution operation, I denoted it in a discrete fashion, because usually the images that are captured in any system consists of pixels. So it is nothing but a matrix. So every image is kind of a matrix, and here, but we are doing some analytical uh, uh, exercises to determine certain like properties of the system. So we will stick to continuous modes, and here you can see we can define now the intensity of in the blurred image in the form of this double integral, where IF is your focused image, H is the weights assigned from the Gaussian blur kernel, and this is integrated over area, which is reminiscent of a blur circle, or in this case, the region associated with the Gaussian blur kernel is locally spread out. That's why we use elemental area to integrate it. And but we will do this for the whole space of image, because the Gaussian kernel is a smooth kernel without any sharp boundaries. So it asymptotically approaches 0 as r tends to infinity. So here we have a bound of 0 to infinity in the radial direction, and this because we are doing throughout the space in the angular direction, it will be 0 to 2 pi. So this dA can be represented as dr into r d theta, and you can just this is just a standard way of doing it. So with this integral equation, I would just want to emphasize a few things, because you are looking at a lot of parameters like r, rh, rt, and it can be quite confusing. Because we chose a polar coordinate system, it is better to have r and theta kind of configuration fixed at the center of the particle, okay? Because it is easier to define a particle that way. But if you want to estimate the intensity in the blurred image at a location, say RT, radial location RT. So then you have to perform the integral with this center, right? It's in the same way that we did with the matrices, like wherever you want to evaluate the intensity in the final image, you place the matrix at that location, centered at that location, and do the weighted sum and weighted average, whatever, to estimate the value at that location. So here this blue blurred entity represents the Gaussian blur kernel, which centered around this point where we want to estimate the intensity. But to integrate it, then we have to do it in the local coordinate system with RH as the radial coordinate and some theta dash. But to do that, it becomes very tedious. So that what we do is we convert everything in terms of r and theta and use them as dummy variables for integration. So it may sound slightly complicated, whatever I'm trying to say, but just to put it in simple terms, r and theta are the dummy variables of integration and they will go away. And r versus gt will give you the spatial distribution of intensity, where rt is your spatial radius and gt is the intensity at that radial location. Okay, and because of axis symmetry, there is no theta dependence here. And to specify what parameters depend on what, as I've said that gt is only a function of rt, or intensity is only the function of radial position rt. If or the focused image is a function of r only, because in that coordinate system it is the easiest to define. And h, your blur kernel, is also should also be defined in r, because as I told you, we have to convert it in terms of r so that we can integrate it, but at a given rt, because that rt dependence should stay here, right? Because then only the both side of the equations are function of rt. And this is just depicts that r and theta are your integral parameters, or just dummy variables for integration. Now coming back to blur kernel, we know this form of Gaussian blur kernel, but you can see here we have used RH to define this kernel, right? Because the kernel is centered around this point where your local radial coordinate is RH. So that's why RH comes up here. And from simple trigonometry, you can show that RH is dependent on R and RT and theta in this form. So it is fairly simple to solve. You can try that. And also one more parameter that we have is we know what is the functional form of this if. We know that when r is greater than the diameter of the radius of the particle, this function goes to 0. So this modifies the limit of the integral. Now we don't need to solve the integral beyond d naught by 2. So we don't need to solve it from 0 to infinity. We just need to solve it from 0 to d naught by 2. And substituting everything, and also in that range, this if is just 1. So if just disappears here because it is always 1 there. And this is your blur kernel, and this is your dA, and these are your new limits. And this is now the integral equation, which is of which represents the blurring of a circular particle. This is what we use in a specific technique called a single camera depth from defocus. So we will go there shortly, but we can just numerically solve this to estimate the blur distribution, and that's what we are going to do next, to get some intuition of how the images look at different extents of blurring. Now apart from this equation correlating like the various geometrical parameters like the dependence of intensity on the radial position, we have an intrinsic parameter, that is sigma, which represents the extent of blur, right? And we have already seen that this extent of blur or deep focus is dependent on depth, and we have used geometric optics to arrive at this equation, which relates both of them. So this big term that you see in front of it, if you don't see change the aperture of your system or other some parameters associated with your experimental system, this will remain a constant, and it shows us that this sigma is directly proportional to your mod delta z. And by mod delta z, it is also very critical to visualize or understand this mod sign. It tells us that blurring is symmetric across the object plane. So if you are to like if you move away from the object plane, there are two directions in which you can move. You can move either towards the camera or away from the camera. So if you move by the same amount in either of the direction, the blurred image should look exactly the same in this assumption. So the way we assume things to be, it comes out to be like that. And in certain specific experimental setup, we can achieve this. And that is what makes this system very interesting. Although it is still an idealized system, in a practical systems, it is not always true. But yeah, this mod sign tells you that your blurring is symmetric in the Z direction. If you go either towards the camera or away from the camera, you will get same amount of blurring if you shift by the same amount in the depth direction. And this equation is the one that relates depth with defocus and is the motivation for the development of technique depth from defocus. Now coming to this defocus blurring, the model that we have used, we will use it to generate some synthetic images. So we just took a circle like this. As I've told you, we assign an intensity of 1 to the particle and intensity of 0 to the background. And this is the focused image where sigma is 0. And if we apply the equations that we solved earlier, at each pixel location and numerically solve it by certain discretization, we can get this blurred images for different extent of blurring. And this was done as we have seen using a Gaussian blur kernel. So here we write it in terms of the fraction of particle diameter, because if even if we change the particle size, it will have that geometrical similarity and it will look the same. So if we blur it using 10% of the particle diameter, it will look something like this. And if we blur it using 50% of the particle diameter, it will look extremely blurred, right? And you see that even the intensity goes to a lower value, because this is still kind of a moving average operation with certain weights assigned to it. And one more interesting or important thing to note is, here you have a sharp interface, so you can clearly demarcate the boundary. But here there is no boundary. Visually you can still say, okay, the particle is somewhere here, but to estimate it quantitatively, it's still a challenge. So the images that I've showed you in the last slides actually correlates pretty well with the experiments. And when I say experiment, what kind of imaging system am I talking about? So for the dispersion size measurement using imaging, the shadowgraphy or shadow imaging is the most suitable candidate, where what you do is you use a backlighting. So what do we mean by backlighting? It means a strong light source placed directly behind your object of interest, which creates extremely strong shadows. So it is represented here in this diagram. You have a light source, you have the object, it is in line with the camera, and the light source is placed behind the object. So it forms a shadow which is captured by your high-speed camera. So your background is usually bright and it has small features as shadows. So if you have a droplet, it will look something like this if it is in focus, where your background is bright and the shadows are or the droplet is visualized as a shadow. But if it is defocused, or if the particle is away from the object plane, it looks blurred. So here you have sharp boundaries and it is very easy to estimate size, because you can directly take the diameter, right? Or you can estimate the area and use the formula root over of a by pi, something like that, to get an equivalent radius. But here you don't have any of the boundaries to detect the size, right? So the boundary is extremely smooth. So how will you mark size here? So that becomes a challenge. And also you may have a question that if we have droplets, say, of water is transparent, right? So how will the shadows look? Then these systems are useful if there is a large refractive index contrast between the matter of the particle and the surrounding matter, that is mostly air, or it can be anything else also. There can be a lot of different kind of dispersions, right? So if your refractive index contrast is pretty high, then that still leads to formation of these sharp shadows. And Yeah, it is because of something that is known as like ball lens effect and things like that. So you can look it up, but it'll look like a shadow. That is for sure. Now that we have seen that how shadow imaging is done and how particles look in those images, say we have a particle at in focus here, and we shift the particle from the object plane by certain distance delta z, and it becomes defocused. We have seen that there is no boundary associated with it to determine its size. So now we will develop a approach that is known as thresholding approach, where we can determine an effective size for the particle, which might not be the true size of the particle. So before going to that procedure, we normalize the image, as I have discussed earlier as well. We rescale the image from 0 to 1, where 0 values are assigned to the background. In the shadow imaging system, the backgrounds are usually bright. So the brightest points are set to 0, and in shadow imaging, the darkest points are associated with the particle. So there we will assign a value of 1. So this is the operation that we will do for normalization. And these image intensity values are also known as gray level intensity, because these shadows are usually, we don't want the color of these shadows, we only want the intensity values. So we collect only a monochromatic signal, and that's why we call it as gray level values, because it's just black and white or grayscale. The next step is thresholding. What do we mean by that? It is a logical operation where we assess if the logic is true or false. So we define a logic in a way that you choose a threshold value, say 0.5, and at each pixel location you determine if the intensity at that location is greater than 0.5 or not. If yes, you assign a value of 1. If no, you assign a value of 0. All the ones together collectively form a mask. So that is the idea. So here in this normalized image, at each pixel location, we see if this logic is valid or not, and all the collective points where this logic is valid looks like this yellow blob. So in this yellow blob, the intensity was greater than the threshold value, and that is something that is known as a mask. Okay, and we can now see that this mask has a distinct boundary, so we can determine its size. So here we can determine its size, and that is something that is known as a thresholded size. And clearly it will be close to the particle size, but not the same. We will see that how. So here we have taken particles with different extent of blurring, as I've showed you earlier, and we chose a threshold value of 0.5 and see what is being detected. So for the same particle, okay, so these are the images for the same particle but with a different extent of blurring. So the first one, where the blurring is 0, the thresholded size is same as the particle size, right? Because there is no blurring. But for the case where there is some blurring, say 10% of the particle size, by the extent of 10% of the particle size, we see that still you can see the particle image is not that blurred, and this thresholded size is roughly the same as the particle size. But now in this case where the particle is like slightly more blurred, and you can see it is not resembling the actual particle, here we can see that the thresholded size is smaller. It's now smaller than the actual particle size. Why is this happening? Because the convolution using a Gaussian blur kernel is similar to a weighted moving average, and it smooths out features. So at each and every point, the intensity goes to a much lower value than the initial one if your blur kernel strength and size is very large. So that is what is happening. So there is now a smaller region where this logic is valid. If you go to even higher blurrings, like 0.5 times the particle diameter, which is like a extremely high blurring, you can barely see the particle here. It looks like just a rough patch in the image. Here, there are no pixel values where your intensity is 0.5. So no particle is being detected here. You will detect nothing using this threshold. So this tells us something very important. That thresholding does not give you the exact particle size. Depending on the extent of blurring, it will deviate a lot, and it will always be less than your original particle size. Secondly, there is a particular extent of blurring beyond which the thresholding will give you nothing. So there is no particle detected. So it basically tells you that as sigma is related to depth, so if your particle goes beyond a certain depth, it will not be detected, and that marks your detection depth. So we will discuss about that more later. The second point being the choice of the threshold. Say you have this particle which is blurred by zero point 0.3 times the particle diameter. If you choose a threshold of zero point 0.3, it looks something like this. If you choose a higher value, it looks smaller, and if you choose even a higher value, it looks even smaller, because high intensities are still preserved at the center, but it is smoothened out as we go out, and it decreases smoothly as we go radially outwards, right? So here you can see the choice of threshold also plays a critical role. So the effective size definitely cannot be directly predicted using a threshold. Particularly in this case where the blurring is very high, you can see that as it earlier also we have seen that it was not getting detected for 0.5. It is still being detected for 0.3. But if you choose a higher value of threshold, it will not be detected. So the even detection depth will be dependent on what threshold you choose. So both the apparent size and detection depth and all these things are not universal and cannot be relied on, although they will give you some idea associated with the size, but it will not tell you the exact size. Now, talking about depth from defocus in the context of particles, it is a two parameter system, because the particle itself can be defined using two parameters, the size of the particle and the position of the particle, which is something which we want to determine. Uh, and we have is a blurred image of the particle. So in that blurred image, we have to somehow quantify the defocus and then correlate that defocus with the depth, and that's how the depth from defocus technique can be applied to this two parameter system. Before going into that, let us understand how the blurring increases for particles. So we have seen that if the particle is moved away from the plane of focus, or the object plane as depicted here, you will see that it will become more and more blurred, right? So the extent of blurring increases. Uh, with the increase in extent of blurring, the threshold diameter decreases. So that is also that we have seen in the last few slides. Apart from that, the size of particle is also something which is important. So say if you have particles, all the particles stacked in the same plane, okay, they are all on the same plane, which is away from your object plane. So basically all the particles are moved away by the same amount of depth, but you will see that the larger particles will be blurred less and the smaller particles will be blurred more. So for the same delta z, decreasing d naught also increases the extent of blurring. So there are two kind of independent self-contradicting parameter kind of thing, which shows that blurring can be controlled either by depth or by the actual size of the particle. So that's why these two parameters are extremely important in the system, not because just we want to know it, but also because they affect the amount of blurring. Uh, in this way, for a fixed intensity threshold, say 0.5, this thresholded size is a function of depth and particle diameter, some implicit function. It can be linear, non-linear, we don't know for now. And if we want to see this as a system of equations that we are trying to solve, so we only know there is this one equation or functional equation which relates these three parameters, but for now we don't know the functional form of that. Apart from that, we also know the particle size and particle depth. All we have is dt, or thresholded size. So we have only one known parameter, one equation that we know is existent, but we don't know its functional form. And the things that we want to determine out of it, or the unknowns, are the particle size and the depth. So we have insufficient information or constraints to solve this problem at this stage. So the next obvious step is to generate more equations and collect more information. In that way, you can determine these two parameters, the depth and the size. One approach of doing it is using two cameras, and we will still apply the thresholding approach, but we will capture two simultaneous images of the same particle with a different extent of blurring. And how do we do that? For that, we choose the imaging system in the same way that we have shown earlier. The only difference being there are two cameras. So we put the two cameras in a way that the imaging plane are offset by some delta value, so they are not aligned. So for the same particle, two different images will be formed. So this is the particle P. On the imaging plane 1, you see it is blurred by some extent to R1, and in the imaging plane 2, it is blurred even more by some extent to R2. So it looks something like this. So these are actual experimental images. You can see when focused, the particle looks like this. In the imaging plane 1, it looks like this, and in the imaging plane 2, it looks like this, and there is a different degree of blur captured. So now if we have two simultaneous images with a different degree of blur for the same particle, and we can use it to determine the actual particle. So for the camera 1, like, we will have this functional form that we were discussing earlier. For camera 2, we will have this functional form. As the extent of blurring is different, the thresholded sizes will be different, and the delta z will also be determined based on their respective object planes. Okay, so now we have two equations. Like, we know there are two equations, but we still don't know the functional form, and we have two knowns now. So we have this thresholded size from the two images, but we have now, like, the same two unknowns, like d naught and the position z, but we have two functions which we don't know how they look, like the functional forms is not known. So still it seems like we don't have enough information to solve the problem, but it looks like we are going in a right direction. So the next step now is to determine the functional form, because if we have that, then we have the proper system where there are two calculated known parameters, two functions, and using those system of equations, we generate the two outputs or unknowns, that is the size and depth of the image, or the particle. How do we do that? We perform calibration. We use a calibration operation to generate those two functions. And how do we do that? First of all, this shows the operation that we do. We take target dots of known size, place it in the plane of focus first. So it will look something like this. Say in the camera 1, I'll talk about camera 1 first. So we will now move it to a different depth location, say this point, and we will get a blurred image. We know exactly this depth location, so we track this depth location. So we will move it another step to a different depth location and capture the image again, and we'll do that on one direction, and we'll do the same in the other direction as well. So now if we choose a threshold, say 0.6, and plot the thresholded diameter with the depth positions, we get a curve something like this. These red points represent the curve for the camera 1. Now for the camera 2, the same curve will be replicated, only offset by a certain delta z. That delta z is related to the offset in the imaging plane, because the imaging planes are shifted. So you will get the focused image slightly away from the camera 1, which is somewhere here. So this is the plane of focus for camera 1. This is plane of focus for camera 2. But you will get the same curve, just shifted, because all the rest of your optical parameters remains the same. So this curve is the calibration function that correlates dt with z, and we get a functional form something like this, two functions from this, and in this map we can fit a curve to get the calibration function. So this gives us the two equations, the functional form of two equations, which looks like an inverted parabola, and actually we fit a sixth order polynomial usually in this. And now we have known parameters, two thresholded diameters, and now there are two unknowns, that is the size and depth. and it looks like a sufficient condition now for the problem to be solved, and which is true. So this as these two are like kind of not linear and like just shifted, but they are sixth order polynomials, we have to use some numerical jugglery to solve these the two equations with two knowns, but we can do that and estimate the actual size and depth of the particle. And to do that experimentally, how do we place two imaging sensor planes with a fixed offset or a predetermined offset? That is done using a splitter plate. So we have this backlight imaging system. So this is the light source. It comes like this through the measurement volume and comes over the lens. After the lens, we place a splitter plate that divides that light beam into two parts, and we can now take and place the cameras in both of these paths. And by changing the position of the camera, we change the path length or we change the value of S. So in this image, you can see this box consists of the splitter plate. This is the lens. This is the light source. This is camera 2 and this is camera 1. So the splitter plate moves one beam here and one beam here. Here what you see is an orange band or ring. That is the spacer. That is what is adding an extra value of S in this direction or extra path length in this direction. By that we get two planes of imaging with different path lengths. And this problem uh, like is particularly related to shock induced droplet atomization, and there we implemented this two camera DFD to estimate the droplet sizes. So here are the results that we obtained. So the top video actually shows you the droplet disintegration and formation of a lot of daughter droplets. And the bottom one shows a zoomed in view, like the actual ROI where we did the measurements. So here you can see a wide array of droplet sizes and also the extent of blurring. So they are volumetrically distributed and they all show different extent of blurring depending on their size and position. So we normalize the image, identify these particles or droplets, and then apply our technique to get the effective sizes, like the thresholded sizes from the two cameras. And we generate a calibration curve before doing these experiments, and then feed these two values to determine the actual particle diameter and the position. For this particular problem in hand, the position is not that important. We are interested more in the size distributions. So that can be plotted in terms of a probability density functions, which is nothing but a normalized histogram. So you define bins, and in each bin you count the number of droplets that appeared, and you normalize the whole thing in a way that the area under this curve is 1. So you will see that as we increase the Weber numbers or the shock strengths, the smaller droplets are produced. The only limitation set to this system is the resolution in space and time. So this DFD technique can be, that's why, applied to very high speed phenomenon if you have high speed camera. Apart from that, the limitation is not there because of say like a lot of droplets distributed in a volume, which is typically the case in Doppler measurements where only point measurements can be done. Here a volumetric measurement is being done. So that is a advantage that we have. And this advantage of volumetric measurement we can quantitatively estimate as well, which is even more important. And how is that? First of all, what do we mean by detection depth? As I've told you earlier, that here are, say, the larger particles which are moved away from the plane of focus, and you see they get blurred. And when the smaller particles are moved away, you see they get blurred much faster and disappears almost here. So you see that the region till which they can be detected is bound by this dotted line. And even in the experiments, we see that in the shock experiment that I've showed you earlier, if I plot all the points and plot their position that we have estimated and the particle size, we see they are inside this envelope and the boundary is just a line. So this line can be represented in the form of some parameter alpha, and this is the line of detection depth. And if we take it in both the directions, it marks the measurement volume. So with this, we can exactly know what is the measurement volume. If we know alpha, we can know exactly the measurement volume, and that is done in this way. So you are capturing particles in the region of interest, which is this, and in the depth direction, that is this. And the particles on the edges are neglected. So we usually take the effective frame of view as the actual A by B of the FOV minus the particle sizes. So this is the effective frame of view, and in this, if we multiply the detection volume, detection depth, then we get the detection volume. So we know for this particle size, for that particular particle diameter, the detection volume goes like this, and if we change the particle size, the detection volume changes. So we have an exact correlation between the detection volume and the particle size, which is very crucial. So, as we have seen that larger particles are detected over larger depths compared to smaller particles. So, the measurement volume associated with larger particles is bigger. So, we are seeing them more often than smaller particles because of this bias. And this oversampling of larger particles must be corrected. And how it is done? That instead of counting the number of particles in each bin in the histogram, we can count the number of particles appearing per unit volume. So if we regularize it using per unit volume, then irrespective of the size of the volume, we are averaging it, kind of thing. And in that way, we can correct it. So the undersampled small droplets would be corrected to appear as per unit volume thing, and that is reflected also in this plot. You can see after corrections, the number of smaller droplets went up. And how did we achieve that? You can see that here in the equation. In earlier, we were only counting the number of particles in the bin di, and now we have normalized that frequency with the volume measurement volume associated with that bin di. That leads to this number concentration of particles in that bin. And when that is substituted in the probability distribution function, we get this corrected function. So in this way, this knowledge is extremely important and is useful for not just for bias correction, but also to get a number concentration of particles in your system. So with this, our two camera DFD measurement is over, and in the next lecture, we will see what other kind of DFD techniques can be developed or implemented.